Hello everybody, and welcome back to another geometry lesson. Today we're taking a look at section 8.3, which is proving triangle similarity using SSS and SAS, two things which may sound pretty familiar to us. Now, last class we talked about how to prove that triangles are similar using angle-angle similarity, two angles that match across the two triangles. Today we're going to learn two other theorems that show that two triangles are similar. And you may already know what the letters stand for. So let's start with side-side-side similarity theorem. I'm going to draw a scalene triangle like so. And I'm going to draw a scalene triangle that we can assume is probably going to be similar. Like so. I'm going to also label these triangles for our reference. So this is triangle A, B, C. This one is D, E, F. The idea here is this. If we can compare the different side lengths of these and know that they are proportional to each other, the two triangles are similar. Now, as a reminder, what does proportional mean? Well, proportional means, for instance, that if this side is 3, this side might be 6. Okay, maybe this side is 4, this side is 8. Maybe this side is 5, this side is 10. The idea is, if there is a scale factor to go from one triangle to the next, in this case, k would equal 2, since we're multiplying everything by 2, then the triangles have to be similar, as long as it's the same scale factor for all three sides. So the way that we would show that these two triangles are similar is by writing out a statement of proportionality, something that we did in 8.1, but it's been a moment. A statement of proportionality compares all the different side lengths that are corresponding to each other and sees if they make the same fractions. For instance, we know that DE, this side length of 6, corresponds to AB, the side length of 3. 6 divided by 3 is 2, so we can assume that the scale factor is going to be 2. EF is 8. BC is 4. What's 8 divided by 4? Well, it's also 2. And of course, FD being 10 and CA being 5 means that when they divide, they're also going to make 2. In other words, as long as all three sides are proportional, or three pairs of sides, I should say, are proportional to each other, meaning they make the same fraction, the triangles are similar. In words, the theorem will look like this. If the corresponding side lengths of two triangles are proportional, then the triangles are similar. If the corresponding side lengths of the two triangles are proportional, then triangles are similar. This bodes really, really well for problems like in example 1. So let's take a look at that. Example 1 is asking us which of the below three triangles are similar. So we're trying to track down if ABC is similar to DEF, if DEF is similar to GHJ, or if GHJ is similar to ABC. There's a lot to keep track of here. Here's my suggestion for how to do it. In order to see if triangles are proportional, we should compare two at a time. So let's start by comparing the first two triangles, ABC to DEF. We're going to either be able to say ABC is similar to DEF or ABC is dissimilar to DEF. Dissimilar just means not similar. And the symbol for it is going to look like our similarity symbol with a slash through it. So let's compare these two. The problem is it can be a little bit difficult to decide which lengths to compare. I have a hint for you. Even if we don't know for a fact which side lengths match up with which side lengths, we can compare to see what the longest sides of both of them are, right? So the longest side in triangle ABC seems to be this 16. I'll label it long. What's the longest side in DEF? Well, between 6, 9, and 12, the longest one is 12. So that's what we are going to be comparing. We are going to be comparing FD to CA. Similarly, we can take a look at the smallest length in both of them. 8 is smaller than 12. 6 is smaller than 9. So we're comparing 6 and 8. And finally, we've got our medium length here of 12 and our medium length here of 9. I'll call this the mid-length. So all we need to do now is set up some proportions to see if they equal the same scale factor. Let's do it. I always go second over first. In this case, that'd be DEF divided by ABC. In this case, we have 12 over 16, which, if we simplify this fraction, equals 3/4. Okay, so the scale factor so far we think is 3/4, but we need to check the others. 6 over 8 is what we'll do next, because 6 is the smallest on the second triangle, 8 is the smallest on the first one. So we do 6 over 8, and oh, wouldn't you know it, it's also 3/4. Cool. Last but not least, we compared the medium lengths, 9 to 12. And 9 over 12 is also 3/4. Cool. What this means is this. Our statement of proportionality is true. We can absolutely say that FD over CA, because those are the long side divided by the long side, equals EF over BC. That's the medium over medium, equals DE over AB. Since our statement of proportionality works out, we can give the go-ahead and say that ABC is similar to DEF. Now here's what I'd like you to do. I'd like you to pause the video and try to compare the next two triangles. I want you to compare triangles DEF and GHJ to see if they are similar or dissimilar. Pause the video and try it out. How did we do? Hopefully we saw that we would be comparing 16 as our long side with 12. We'd be comparing 8 over 6 as our small, and 10 over 9 for our medium, which was the problem. 10 over 9 is just 10 over 9. The rest all simplified, that last one didn't. So in our statement of proportionality, I put down not equal to. Thus, we can say for sure these two triangles are dissimilar. They are not similar. Now you might be saying, Mr. Strager, we never compared ABC to GHJ. And you're correct, we haven't. But we actually don't need to anymore, because we can apply the transitive property. We know that ABC is similar to DEF. If DEF was similar to GHJ, ABC and GHJ would be similar. But because these two are dissimilar, we can say ABC is dissimilar to GHJ. Again, we can jump straight to that conclusion because we had a dissimilarity here. And if these are similar and these aren't, the first and the third certainly are not either. Nice. Let's take a look down below. I'm actually going to take a look at part B of example 2. But here's the deal. We are told the two triangles are similar. And oftentimes, especially on tests, we'll actually be told what triangles are similar to what. So for the purposes of this example, we can assume that HK is similar to XZ, HJ is similar to XY, JK is similar to YZ. I'd also like to mention there's a bit of a misprint on these. This should be X minus 6, just to let you know. So in these problems, we're trying to solve for X. We know the two triangles are similar, but we don't know what to do next. Well, normally, if we were solving for a missing side that was just the letter X, we could find the scale factor and multiply through. The problem is here, we don't just have x's. We've got 5 times x minus 6, or x minus 5. The good news is, these are still solved just about the same way. Step 1, find the scale factor. So we look on our shapes to find any side lengths that we can compare. In this case, 15 and 3. To find the scale factor k, we do the second divided by the first, so 3 divided by 15, which simplifies to 1/5. Now for the fun part. We can compare any two of the other lengths to solve for x. For instance, we know that 30, which I'll mark in red, is supposed to be similar to x minus 5. So we know that after applying the scale factor of 1/5, meaning we multiply by 1/5, we should get x minus 5. This is why it's so important to make sure you have your scale factor from dividing the second by the first. That way you can decide which way to multiply. Here, we could write 30 times 1/5 equals x minus 5. Oops, let me zoom out a little bit. Because in order to get to the x minus 5, we have to apply the scale factor. So we can solve this. 30 times 1/5 is 6. So 6 equals x minus 5. And if we add 5 to both sides, we get x equals 11. Nice. But how do we know if we're right or not? Well, there are two locations where there's x's. We could plug it in to this length here and see if it multiplies by 1/5 to make 5. So 5 times 11 minus 6 times our scale factor of 1/5 should equal 5, according to this. Let's see. 11 minus 6 is 5. 5 times 5 is 25. And 1/5 of 25 is just 5 again. Check. We got it. Pause the video and try out example A. In example A, we should have gotten x equals 7. Before we go on to the next page, I'd like to discuss the last similarity theorem that we are going to be talking about in this unit. the side-angle-side similarity theorem. And this is one that should also be pretty dang familiar with us. After all, we have seen it before when we did congruencies. The idea is this, folks. Once again, I'm going to draw two triangles. Let's say I draw one that looks like this, and the other that looks like that, but bigger. The idea of side angle side is this. We know that angles in similar triangles have to be congruent. So start by figuring out if two angles are congruent in the triangles. We also know that side angle side deals very specifically with the sides next to or adjacent to the angle. The next step is to check and see if the sides are both proportional. Let's say this is 2, 4, 6, and 12, for instance. To check if they're proportional, we can do what we always do. We can do 4 divided by 2 equals 12 divided by 6. 4 divided by 2 is 2. 12 divided by 6 is 2. So we know now the sides are proportional. We can say that by side, angle, side similarity, these two triangles are similar. Just remember, it's always the angle in between your two proportional sides. So the theorem goes like this. If an angle of one triangle is congruent to an angle on another triangle, and the lengths lengths of the sides including these angles are proportional, then the triangles are similar. Very nice. So when we take a look at an example like example 3, explaining why the triangles are similar, all we need to do is figure out what sides pair up with what sides, set up a proportionality statement, and see if the angle between two of those sides is congruent. Well, we've already got our angle in this first example here. We know that angle R has to be congruent to angle T or angle N. They're both right angles. So that's the first part done. Be very careful and make sure you pay attention to the statements up above to see what's similar to what. Pn is similar to SR in this case, which we could tell by looking at them. But sometimes I could have Pn be similar to RT, even though they don't look particularly similar. So let's start there. Pn and SR are similar. That means we could probably do Pn divided by SR to find our supposed scale factor. Supposedly, at least. Pn divided by SR is 18 over 24, which is 3/4. Cool. Next length. In these triangles, the length that is next to our congruent angle is NQ. Let me get a little squiggle here. NQ is supposed to be similar to RT. So again, we can try it out. 21 over 28 equals, well, it's 3/4 as well. So Pn over Sr does equal NQ over RT. We would say the following. Triangle SRT is similar to triangle PNQ due to the side-angle-side similarity theorem. Done. It won't always be this easy. I'd like to direct your attention over to part B. Now, I want to warn you, I was very tricky with the way the letters were ordered on this one. So, pause the video, try out part B, and see how we do. This one was a bit of a tricky one. Let's take a look together. So, if we take a look, according to the letters, XZ and YZ are corresponding parts. Reminder, XZW is this triangle on the left, YZX is this triangle on the right. XZ seems to be this vertical length right here. Cool. YZ is this bottom length. So we're actually saying that this here bottom length and this side length are supposed to be corresponding parts. Think of it like this. This is the original triangle, and if we tilted the triangle 90 degrees counterclockwise, it would look like this. It's like we took it and flipped it on its head. So that means that this right angle actually corresponds with this right angle here. So let's do a proportion. We know that 9 divided by 12 is what we'll get if we're comparing the right triangle to the left. 9 over 12 is 3/4. Now we need to find the other sides to compare. Well, if we're looking at this right angle here, the next side that's on the opposite side of it is this one. Wait a second. That's XZ again. XZ comes up twice in this problem. It's just that it comes up at the end of this one, as opposed to the beginning of the previous triangle. XZ is supposed to be similar or proportional to ZW. So since XZ is 12 and ZW is 16, 12 over 16 is 3/4. We know that works. So in short, we know that angle XZW is congruent to this right angle here. This angle is YZX. And we know that just as we have YZ being compared to XZ, the first two letters of both of our statements, we say that ZX can be compared to ZW, the last two. So once again, side angle side helps us prove that these triangles are similar. Cool. In example 4, we are asked to sketch the indicated triangles and determine if they are similar. I'm going to do A here, but I will leave B for you to try at home. In triangle RST, RS is 20, ST is 32, and the measure of angle S is 16 degrees. This is another case where we don't need an exact scale drawing. I mean, I'm drawing angle S here, and it is going to be way bigger than 16 degrees. We can label it as such. So this will be RST. We know that RS is 20, ST is 32. In the next triangle, FGH, we want to take a look at the letters here. RST is this way, and FGH, if I labeled it this way, H would be the angle down here. It's okay, it doesn't mean they're not similar. I mean, this triangle could just be tipped on its side to make FGH. The measure of the angle is 24 degrees. GH is 30, HF is 48. And already we sort of see a bit of a problem. What's the problem? Well, we don't know the third sides here, so we're probably going to use side, angle, side, especially because we know the sides bordering the angles. The problem is these angles don't match. Yeah, these angles do not match up at all. Now, is there a possibility that another one of the angles here could match? Maybe, but we don't have the information to prove that. We can say, because we don't have enough information, these two triangles are dissimilar. Cool. All right. Let's take a look at example 5. Now, I want to warn you before we go into this proof is crazy. This proof is kind of difficult, but we're doing it to make a point. We're doing it to show that we can use these properties in proofs. So let's start with this. We are told that triangle BAC is a right triangle, so I'm going to write that up here. BAC is right. And we're also told that D, E, and F are midpoints. And these are our givens. Cool. From here, we need to prove that angle DEF equals 90 degrees. So, what this means is there's got to be a second triangle here. DEF we can connect up with segments. D to E, E to F, F to D. Hang on a second. This looks a bit familiar. From Unit 5 specifically. What do we call it when we connect two midpoints through a triangle? What do we create? Well, that's a midsegment. A midsegment is created anytime we connect two midpoints in a triangle. And we happen to know a fun fact about midsegments, if we can recall them. If we compare line segment DE to line segment AC, we know that DE, in the midsegment, is supposed to be half of AC, or CA, I should say. That is a fact about midsegments. By the triangle midsegment theorem, we can say that DE equals 1/2 of CA. I've ordered it in this way because D seems to be the long vertex of this inner triangle, and C is the longer vertex of this outer triangle. But wait a second, Mr. Strager, I hear you say. Couldn't we do the same thing with EF? We absolutely can. EF should be half of AB because of the triangle midsegment theorem. EF equals 1/2 of AB. Again, matching up the letters. E matches with A, E matches with A. And of course, we can complete this triangle midsegment, the midsegment triangle, by connecting DF and recognizing that that's going to be half of BC. More specifically, I'm going to say FD equals 1/2 of, since F matches with B, we will call it BC. Nice. And now we are stuck. Yep, we're stuck. The problem is, what we really want to show is we want to show that all the sides are proportional to each other. But instead we've got all these different equations lying around. If we could find some way to eventually combine them all, like this, where we have letters divided by letters, letters divided by letters, letters divided by letters, we would be golden. But right now, we don't have letters divided by letters. We have some letters equaling some letters. So let's ask ourselves, what could we do to our statement DE equals 1/2 of CA to make it look more like this, to make it look like one of our line segments is above one of our other line segments? Well, couldn't we just divide both sides by CA? If we do that, the CA's will cancel here, and we would get DE over CA equals 1/2. And we could repeat that with the other ones too. Like if we divided both sides by AB in this problem, we would get EF over AB equals 1/2, because we're moving the AB to the other side. And we could get FD over BC equals 1/2. What property does this? Well, since we divided both sides by the same thing, this is just the division property of equality that allows us to divide both sides by the same quantity. And now we might see it. This equals 1/2. This equals 1/2. This equals 1/2. All of our scale factors are equal to each other. If they're all equal to each other, couldn't we rewrite this statement as just DE over CA equals EF over AB, which equals FD over BC? I think we can. Because they all equal 1/2, we can substitute one of these expressions in for 1/2. And then we could substitute the other expression in for 1/2. We can all just substitute each other together. This is using the substitution property of equality. And now we're nearing the end. The good news is this. This means that all of our sides are proportional. If the sides of our two triangles are proportional, they must be similar. What theory says that? What theory says that if all sides of your triangles are proportional and the triangles are similar? Well, that is just side, side, side similarity theorem. And now we can put it all together. If these triangles are similar, this inside one and the outside one, we know that each piece of them is similar. We know specifically that angles have to be congruent. So this angle must be a right angle, because this one is. We can say that angle DEF equals 90 degrees. Technically, it's the measure of angle DEF, but whatever. For part 6 here, we can say the following. Corresponding angles in similar triangles are congruent. You don't need to remember the abbreviation for this statement. You can just write that, hey, if the similar triangles, or if there are similar triangles, the angles are congruent. But the abbreviation, instead of CPCTC, corresponding parts of congruent triangles are congruent, We'd have corresponding angles of similar triangles are congruent. Kask. There we go. So that concludes our notes for today, everybody. Thank you so much, and have a fantastic rest of your night.